Okay, we got 2, 1, 0 minutes. Okay, welcome to the next to last lecture before the exam next Thursday. So that's 1 week from today. I hope you all have signed up for the project. A lot of you haven't. The link for this Google Sheet is in emails I sent you. It's also in the syllabus. Be sure to sign up. And when you sign up, if you could put the names of the people that are in your group, the date that you signed up, and please double check the list to make sure that you're not duplicating what somebody else is. Again, the project doesn't have to be that big. You've got up to 5 minutes, but 2 or 3 minutes will be fine for the video. Up to 5 slides, but fewer is fine. Some people have done dances. Some people have done musical interpretation. Whatever you like, you get full credit if you turn it in. But I need the project title by March 15th. And the project itself isn't due until April 22nd. So be sure and put that this is always the last live class of the week, and it's a great way to end the week. Well, thank you so much, James. So just don't forget, this project is meant to be fun. You can choose any astronomical topic at all. It doesn't have to be anything that we covered in this class. Try and pick something narrow, because if you pick like galaxies or black holes, that's such a huge subject. So pick a particular galaxy, or, micro black holes, or, some sort of, or spaghettification, some sort of little detail. You could just take an astronomy textbook, open to the index, close your eyes, point to something, and that's your topic, for example. Okay. So as we talked about on April 29th, then we show the best projects. The best projects get extra credit in the course. Text me if you have any questions. Let's stop the share and choose the lecture. Okay, so here's where we are. We're right here in lecture 12, March 4th. We've got one more lecture next Tuesday before the exam. The exam covers chapter 6, 7, 8, 9, 10, 11, and 12. I have already posted the PowerPoints for all of the lectures. I've already posted the exam guide, and I'll show you in the slides the exam guide. The exam guide lists all of the topics that will be on the exam. Each exam is worth 12% of your grade. This exam is multiple choice, true, false. There's a lot of true, false in this one for some reason. I think it's about 75 questions. Here are the topics in chapter 6. You don't need to write these down, because go to WebAssign resources and it will be right there. Okay, let's see. My camera is black. Shoot. Thank you so much. Yeah, I forgot to change batteries. Hold on 1 second. There we go. Okay. Yeah, I use a DSLR that I have to do it off of batteries. Okay, so let's go back to, oops. There I am. I'm back. Excited. You don't have to write these down. These are in the exam guide that is on website under resources. Today we're covering chapters 10 and 11. So 2 chapters. They're fairly small chapters. And then chapters 12 will be on Tuesday. Chapter 12 is important. There'll be a lot of subject from that. Most of the material is going to be from chapters 6 and 7. Probably half of the questions are on chapters 6 and 7. But here are all the topics that you need. There are 2 topics that are not in the textbook. The first is a question of why are European sirens better? We covered that last time. And the second question has to do with, in fact, I didn't mention this when I was supposed to, so I'm going to mention it now. When they first discovered absorption and emission lines, and that those lines referred to specific elements, they discovered a bunch of lines that didn't seem to correlate to any material that they could find on Earth. And so a scientist said, I think that these lines represent a material that we have not yet discovered. And years later, that material was discovered in the spectra of the sun, and that material was helium, Heli for sun. Okay, and that's how helium got its name. So helium is the first element that was discovered not on Earth but on the sun by using those absorption and emission lines. Okay, and that question is on the exam. Okay, we'll also cover the black body spectrum in the exam in excruciating detail. You won't need to know these equations. You will need to know that the wavelength, this is the Wien equation. You will need to know Wien or Vine, however you pronounce it, sorry. And the fact that the wavelength goes as 1 over the temperature, you need to know that. You also need to know that the total energy flux per unit area goes as temperature to the 4th. You'll need to know that. No calculations, though. You don't need your calculator, but you do need to know these proportionalities. This is the Vine law, Vine, Wien, Von, whatever. And this is the Stefan Boltzmann law. Okay. You need to know what luminosity is. Energy is T to the 4th. And the total luminosity is proportional to the radius squared times temperature to the 4th, the surface area of the star times T to the 4th. And that creates this relationship between luminosity, radius, and temperature. Today's lecture will cover stellar birth and the ISM, the interstellar medium. So really, we're going to talk about where do stars come from. And, you know, this is not a birds and the bees talk. We don't say, you know, mommy star and daddy star got together and formed baby stars. So that's not true, but in fact, it's not true. In other words, there is some truth to the fact that daddy stars and mommy stars do get together and form baby stars. In fact, we are one of those baby stars. If we use to stay close, do you think this could be due to the Earth reaching a different point on the revolution in tides? So Erica just posted a question about her dresser drawer. Short answer is no. The tidal influence is so tiny it wouldn't affect things. So I had the house I'm currently in right now, the house I'm living in, I had built 16 years ago, and there are drawers that were fine 5 years ago that now open of their own accord now, and it's just because houses will settle a little bit and they will not settle uniformly, and so the house will warp just a little bit. Okay. Dang, I thought I was into something. Yeah, no, sorry. By the way, the thing about water going down the drain clockwise in the northern hemisphere, counterclockwise in the southern hemisphere, that is a complete absolute crock. That is an old wives' tale. It is not true. There is a Coriolis effect, but the Coriolis effect affects things the size of hurricanes, the things that are thousands of miles across. The effect that it have on something as small as a drain is actually literally unmeasurable. And the thing about an egg standing up on an eclipse, absolutely, or on a what may I call it? December 21st, a solstice. Yeah, that's just completely false. Okay, here's a picture. This is one of the pretty pictures you see about the universe. The course is called Stars and Galaxies, but there's stuff other than stars and galaxies out there. And in particular, there's what we call the interstellar medium, the ISM. And the ISM is pervasive. Here's a picture of the ISM. The ISM consists of gas and dust, and in many cases, that gas and dust will glow. And so we're going to come back to this exact picture here. You see black here, you see blue here, and you see red here and red here. We're going to explain each of those colors. This is, I don't know. So many, if you take a picture with a small astronomical telescope, they will often stitch those images together. This image is such a nice image. My guess is this was stitched together. And typically this would be a multi-hour exposure. You would not be able to see this with the naked eye. Your eyes just are not sensitive enough. Okay, so today's lecture, we're going to be talking about introduction to the ISM interstellar medium. We'll talk about three types of interstellar medium. There's a whole bunch of different types, but for the purposes of this class, we're just going to talk about three of them. We're going to talk about cold dust clouds, emission nebula, reflection nebula. So there's a whole bunch of detail in today's lecture. And in the guide to the course that includes the formula guide that's posted as a file on WebAssign under resources, I include a little cheat sheet for this course, and we'll go over that cheat sheet in detail. And the cheat sheet discusses the various components of the ISM and the processes that happen in the ISM and the three different types of nebula that we talk about. Now, nebula is a term that we use for a collection of ISM material, okay? Then we'll talk about how stars are born, how mommy stars and daddy stars get together and form baby stars. And then we'll talk about the birth of stars. So the ISM interstellar medium, here is a picture. Test is next Thursday, that's correct. Here is a picture of the Milky Way galaxy. Again, unless you live in Utah, you're not going to be able to see this because it is very, very faint. The thing to notice is that it's really bright, but you see all this dark stuff? That dark stuff is not absence of stars. That dark stuff is the interstellar medium, the gas and dust that actually forms these clouds that blocks our view of the center of the galaxy. And because over thousands of light years, the ISM is very thick, that means we from our position point, we can't see most of the Milky Way galaxy because the gas and dust blocks our view, okay? The interstellar medium consists of two components for the purposes of this class. There are others, but these are the ones that we talk about in this class: gas and dust. Gas is exactly what it sounds like. It's atoms and molecules. It's 90% hydrogen, 9% helium. You are responsible for that. And then 1% everything else. So it's mostly hydrogen and helium, as is the entire universe. The entire universe is mostly hydrogen and helium, mostly hydrogen, a little bit of helium, and then everything else is just noise. We're in that noise, by the way. Now, so that's gas. Dust are particles that are bigger than molecules. It's typically a few thousand atoms. So we say dust, but typically the particles in dust clouds are much, much smaller than the sort of dust that we're familiar with on the Earth. If I look up at well, actually, I can see right now, I'm looking out at the sun and you can see little dust particles floating in the space. Those are millions of times larger than these dust particles. But again, the concept is the same. A dust particle in interstellar space is a clump of stuff, okay? It's a thick clump of stuff. That thickness is important, as we'll talk about in just a minute, okay? So when you shine light through gas and dust, you mostly, although dust is just a small component of the gas and dust, it's the thing that scatters most of the light. So, because if you shine it through a completely gas cloud, for the most part, light will just go through it and you won't actually see the gas. But if there's any amount of dust, what the dust will do is it will bounce the light off, and it will preferentially bounce blue light, okay? So here's extinction. There's not much extinction down here. There's a lot of extinction up in the blue. So here is red, there is blue. Extinction means how much light is taken out. So the bluer the light, the more the dust particles scatter the light. And so what happens is if you're the star and the star is emitting light, the light goes through the dust cloud. The blue photons are scattered and all that's left is the red photons. And so what we see is a red star, although the star is actually white. This is exactly what happens when the sun sets. When the sun sets, it looks red. It looks red not because the sun just turned red. It looks red because the blue light has been scattered by the atmosphere. The atmosphere is now so thick near the horizon that we see that scattering. And by the way, the sky is blue because of that scattering, okay? So the star looks red. This is like a sunset, and it scatters blue light. Okay. And so here is the dust cloud. Now, because the dust particles are thick, and I remember I said all thick particles emit electromagnetic radiation in a thermal spectrum. The same is true with dust clouds. And so, although they're reflecting visible light, they will emit infrared light or radio waves because they're really cold, but they're emitting their own thermal radiation. And that is independent of the light that they scatter. Okay. So here's the scattering of light, and here is their emitting just because they happen to be thick particles. Okay. And again, this lecture has a lot of details. I'll show you the summary page on those details. I apologize for that. Some lectures have equations, some lectures have details. This is the detail course. Okay. So there's three types of nebula we talk about in this course. It's also called nebulae, nebulae, tomato, tomato. And a nebula refers to anything that's fuzzy in the sky. And the term nebula has been around for hundreds of years. And they use this to refer to things that were not stars, were not planets, were just kind of fuzzy balls. Now, we subsequently know that some of those fuzzy balls are galaxies, but most of the fuzzy balls are just fuzzy balls of stuff, of gas and dust. So we're going to talk in today's lecture about cold dust clouds. We're talking about emission nebula and reflection nebula, these three. And again, there's more, but these are the only three that we talk about in this course. Okay, and let me refresh your memory about the different types of spectra. The continuous black body thermal. So continuous, thermal, and black body, those are synonyms. So if you see continuous spectrum, black body spectrum, or thermal spectrum, they all refer to the same concept. And that concept is that continuous hump of radiation that's emitted by all black objects, all thick objects in the universe. Absorption spectra, when I shine normal light through a thin gas cloud, what happens is some of the photons that are shining through that thin gas cloud are absorbed at very specific frequencies, a frequency that's specific to particular atoms in that thin glass cloud, and it produces an absorption emission. So this light is not emitted by the gas cloud, it's emitted by something other than the gas cloud. What the gas cloud does is it takes out photons in absorption lines, as you see. Emission spectra is where light has excited a gas cloud, and so the electrons have popped up, and when those electrons drop down, they will emit light. And in this case, it's the gas cloud that is emitting light. But both this and this, both this and this are thin clouds. This is a thick spectra, okay? So thick objects produce thermal, black body, continuous spectra. Thin objects can either produce an absorption spectra or emission spectra, depending on the details. And these lines, either the emission lines or the absorption lines, are specific to the atoms, the elements that make up those thin clouds. So the interstellar medium, there's three processes that happen in the interstellar medium. This is the cheat sheet. Are the absorption and emission spectra inverse? Yes, that's exactly right. They are exactly the same frequencies. Even space has pollution, but it's made of molecules. That's correct. There are some molecules in outer space, mostly atoms, but there are molecules out there. They've even found formaldehyde, for golly's sake. Okay. So the three processes: thermal, black body, or continuous radiation through a dense body. The second is photon emission, which are the bright lines from a thin hot gas that has where the electrons have been put up a level and then they're bouncing down. And then photon absorption, which are the dark lines through a thin cold gas. These are the three processes. These processes happen other places, more importantly for us, through the atmospheres of suns. But these are the three processes that are also important for the interstellar medium. The nebula, the three types of nebula that we look at are made up of gas, which is atoms and molecules, and there are lines possible. So with the gas, you can either have absorption or emission lines because these are atoms and molecules, and then dust. Dust are thick particles, which there are not very many of them, but they do most of the reflection. But because they're thick, there are no spectral lines associated with them. So here are the processes for the interstellar medium. Here are the components of the interstellar medium. And here are the three types of interstellar medium that we talk about. Is the color of the photon related to the frequency? Absolutely. Yeah, that is real important. Go back to chapters 6 and 7 to go over that. So for everybody else, a red photon is a bigger wavelength or a shorter wavelength than blue. Does red have a longer wavelength or a shorter? That's correct. Red has a longer wavelength, a lower frequency, a lower energy. That's correct. You definitely need to know that for the test. You also need to know that for life. It's important that when someone says, "Oh, I see red light," is that higher or lower energy? You can say, "No, that's lower energy than blue." Okay. And then they will all be astounded. Okay. The three types of nebula: the cold dust cloud. A cold dust cloud will reflect blue photons preferentially. It will also emit thermal or black body radiation by itself because it consists mostly of dust, or at least dust is the most important component of it. Yeah, so fire is a little confusing because so blue fire is definitely hotter than red fire, and it's hotter, it's got a shorter wavelength, higher frequency, and much higher energy. And people associate blue with ice, but don't think that. Think of blue flame. Blue flame is always hotter than red flame. So a cold dust cloud reflects blue light, passes red light, and so it reddens and dims light that passes through it. An emission nebula is a thin, hot gas, and it's typically hydrogen and produces. We see the emission nebula as orange because that is the hydrogen line that's in visible light. And it's typically heated up by ultraviolet radiation from nearby new stars. And then the third is reflection nebula, which is the reflected light from a cold dust cloud, typically blue. It's the blue light that's reflected from that. So cold dust cloud and reflection nebula are kind of the mirror images of each other. And emission nebula basically is a marker for something really energetic and exciting is happening in the neighborhood. So let's talk about cold dust clouds. The average temperature is very cold, a few tens of kelvins above absolute zero. So here it is in visible life, and you can see it's dark, but here it is in infrared, and you see it's glowing in infrared, okay? So that was cold dust clouds, emission nebula, and over here, this red are all emission nebula. It's a hot star, typically a new, very hot blue star that's illuminating the gas clouds. It excites and heats and ionizes the gas. Then when the electrons fall back to the ground state, they produce those emission lines. The gas is thin, so there's no thermal radiation. It's all line radiation. And it's red because it's mostly hydrogen, and the lines in hydrogen that are in visible spectrum are red lines. Okay, and so here the emission nebula, the ultraviolet radiation from the hot stars that are nearby will excite the electrons in the hydrogen gas in the gas nebula, and then those lines will drop down and produce these lines and produce red. If fire can be blue, but why is it not as hot as the sun? Why is the sun not blue? That's wrong. The blue flame is somewhat hotter than the sun. Okay. So the sun is at 5,800 degrees. If you see a pure blue flame, it's hotter than 5,800 degrees. If you see a red flame, it's colder than 5,800 degrees. Okay. Okay, so that was cold dust clouds. That was emission nebula. Now let's talk about reflection nebula. This is a reflection nebula. Notice how blue it is. The star illuminates a gas and dust cloud. The light is reflected by the dust. It appears blue because blue light is scattered, whereas the red light passes through. So here is the star. The red light passes through it, hits the telescope. the blue light is reflected by those dust particles. Okay. So here is the cold dust cloud. Notice it's so thick here, it's actually blocking the light. And here is the reflection nebula, where we're looking off to the side of that nebula and we see the blue light that's being reflected. That's correct. Many of the images of deep space are incredibly beautiful. Okay. Now, this is a very interesting series of images. What I find amazing about that is the star at the center is oscillating in luminosity. And as it oscillates, it increases the illumination and decreases the illumination of the surrounding interstellar medium, okay? And because this interstellar medium is light years across, and this is oscillating, once every few weeks, what you see is it's on the Earth, when something increases or decreases in brightness, everything gets brighter or dimmer at the same time because everything is so close. But here, the gas and dust cloud is so big that only portions of it are illuminated, and then the portions that are illuminated, that illumination will spread as it passes out. So this cloud glows because of the light from that star. And as that light from the star varies, the cloud will vary its light output, but it varies its light output only in the specific part that that light was supposed to reach. So if the light spikes up for 1 week, that spike up of light will only be able to go out 1 light week from the star, okay? Because light travels at the speed of light. And that part where the light was increased, as time goes on, that 1 week of brightness will then move out farther and farther away. Okay. It's just, yeah, so Matthew, this isn't really a shock wave, because this is just really a light echo wave is what they call it. A shock wave is where the matter physically moves and slams into stuff. And we're going to be talking about shock waves in just a few minutes. This is a light echo wave. This is a real image. These are real photographs. What would space look like without dust clouds? It would look like just a bunch of stars. Okay, but there's no place in space that doesn't have gas and dust. Okay, so here's a summary of this. You've got hot young stars that are illuminating the gas and dust around it, heating it up, and as it heats up, it emits radiation in thermal, in spectral lines, and produces an orange emission nebula. Then that light goes and hits a dusky cloud, and on the other side of the cold dust cloud, you'll be able to see through it, but it'll just be red, okay? Because only red light passes through it, unless it's really thick, in which case no light passes through it. If you look off to the side of this cold dust cloud, and it's being illuminated by light from someplace else, then we'll see the reflected light, which is blue. So red light going through it, blue light scattered off at an angle, okay? So that is an emission nebula, a reflection nebula, and a cold dust cloud. The 3 categories that you're responsible for. So here is the Milky Way galaxy. Here's a blow up of that section of the Milky Way galaxy. And now we're going to blow up this section of the Milky Way galaxy. And that brings us back to this image: the dust cloud, the reflection nebula, and the emission nebula. Can these clouds of gas and dust turn into gas giants? Absolutely. And we'll be talking about that in just a couple minutes. Okay. So this is the exact image we started the lecture with, and now we're finishing this part of the lecture with. Now let's launch into, we're going to show another video. This is known, not surprisingly, as the Horsehead Nebula, and we're going to travel to it. The Horsehead Nebula is definitely a cold dust cloud, as you can see, but surrounded by emission nebula. And notice, not all emission nebula is orange. There's other stuff that will glow, that will create different colors. Oh, actually, I take it back. These are reflection nebula for the most part. Okay, so let's talk about the birth of stars. A star is born. And how many times has that been remade? I heard the latest one's really good. Okay, this is called the Pillars of Creation. This is one of the most famous stellar nursery pictures that Hubble ever took. We'll talk about that in a little bit. So stars are formed by these clouds of gas and dust. These gas and dust clouds have to have a reason to collapse and form stars and cloud, because typically they're so tenuous that they don't really have a gravitational force. So they have to be made a lot more dense. One of the ways they become a lot more dense if there's a shock wave. Literally, like a shock wave is like an ocean wave that you see hitting the shoreline. Those are literally shock waves. A shock wave when an airplane goes really fast, where the air just can't get out of the way, that produces a shock wave. And these shock waves in interstellar space are caused by stellar explosions, typically nova, supernova, hypernova, things that blow up. And when they blow up, they spew material through the interstellar medium at extremely high speeds. And this material then compresses and collapses other material. It collapses the material so hard that it creates a density that's high enough that it starts pulling itself together through its self-gravity, through the gravity of the material itself. But it needs that spark. Now, these shock waves are probably the majority of the way that stars are formed, but there's lots of other ways that these gas and dust clouds become denser. So cold clouds tend to be red, whereas hot clouds tend to be blue. No, that's exactly wrong. Cold clouds tend to be red because the cold dust clouds will reflect the blue light that passes through them. Blue clouds are also cold, but they're showing the reflected light. Okay, so don't confuse this with thermal radiation. These cold dust clouds also have thermal radiation, but they're so cold that their thermal radiation typically is in radio waves or infrared that we can't see with the naked eye. What we can see are blue clouds. Those are reflection clouds from very cold things. It's just like when I look at you, I'm not looking at your thermal radiation, I'm looking at your reflected radiation. And if you painted yourself blue, then you would look blue. It's not because you're really hot, it's because you're reflecting blue light. Okay. Does that only depend? Yeah. So Camille, I know it's confusing because we talked about blue being hot and red being cold. That's only for thermal radiation. It's not for reflected radiation, and it's not for line spectra. Okay. So here, a passing shock wave, typically formed by exploding stars, will collapse dust and gas and dust so much that they will then start to collapse on their own. So there are other triggers, such as galaxies colliding is certainly a trigger for gas clouds to compress. We have density waves and galactic spirals. We'll talk about that in future lectures. But here the gas and dust cloud starts to collapse. And as it collapses, it forms this disk, as we've talked about why things always form in disks, because everything has angular momentum. And as it forms this disk, it starts to collapse more and more. And as it collapses more and more, it heats up. It heats up because of the same reason that diesel engines work. Diesel engines, unlike gasoline engines, work because you put in fuel and air into a cylinder, you compress the cylinder. As you compress the cylinder, it heats up. And when it heats up to a certain level, it reaches the ignition temperature of the fuel and mixture, typically a couple thousand degrees. It explodes, it pushes the piston down, and you have a diesel engine, and you can go down the highway. So compressing gas and dust will heat it up until you reach the ignition temperature, which is true for diesel engines. It's also true for stars. So here are pictures of various protostellar disks. And these stars will create birth. There's 14 stages to stellar birth. You are not responsible for these stages. I know the textbook has like 14 stages. I'm just responsible for the basic outline here. And the basic outline is you've got a bunch of stuff. It compresses to smaller and smaller radii. It goes from 10 to the 14th kilometers down to 10 to the 7th kilometers. It's a factor of 10 million in size. And as it collapses, notice that the temperature goes up really hot. This is just like a diesel engine, except instead of going from 400 degrees to 2000 degrees, it goes from 10 degrees to 10 million degrees. Okay. And it takes a few million years to do so. This, for a star the size of our sun, it takes about 10 million years for it to collapse. Okay. Which, as things go on the sun, is relatively quick. And notice here, the central temperature, the temperature or the core of what we call protostars. A protostar is a star before it's a star. So, you meet someone who isn't famous yet, you can call them a protostar. Central temperature goes up to 10 million degrees, whereas the surface temperature only goes up to 4,500 or 5,000 degrees. Okay. So notice that the central temperature goes up a lot faster than the surface temperature. And so we can map these protostars on your favorite and my favorite diagram, the HR diagram. Okay, so here is temperature and there is luminosity. And there's two maps of the HR diagram. On the HR diagram, a gas cloud will have very low luminosity, very low temperature. And then as it collapses, the luminosity will go up and up as the temperature goes up and up, and then it will form this swath down and come down here. Okay. So actually during the formation, it's going to be very, very large, but it actually is a higher luminosity than it is as it comes later. A higher luminosity, but it's still going to be relatively cool, at least the surface temperature. Surface temperature here is about 3,000 degrees. And remember, the HR diagram is mapping not the core temperature, the center of the star, but the temperature at the surface, just because that's what we can observe. Okay. So all one solar mass stars follow this exact same pathway. Okay. Let me repeat that. All one solar mass stars follow this exact birth pathway. In other words, if you know the mass of a star or a protostar, I can tell you its entire past, present, and future. The only thing that determines the past, present, and future of any star is its mass and its mass alone. Now, that's not strictly true. There are other minor details, but in broad strokes, that is true. And this is definitely not true with humans. Humans that all weigh the same often will follow very, very different life paths and have very, very different paths. So the analogy between humans and stars isn't perfect. Okay, so here are the birth lines for different masses. So this was the ending birth line for one solar mass, the ending birth line for 2, for 5, for 15 solar masses. Note here, the birth lines terminate at a specific point in the main sequence. Once the protostar has hit the main sequence, a star is born and it stays there for billions of years. It does not move on the main sequence. So the protostar will come up on the HR diagram, it will come down, and then it will spend most of its life sitting there watching TV, drinking beer, petting the dog, and staying on the main sequence, in our case, for 10 billion years. So in 10 million years, it's really excited. It gets born, it follows down the path, and then it hits the main sequence. And for 10 billion years, it does nada. It does nothing. And then things get really exciting when it's dead, but that's going to be a future lecture. Okay. Great job, star. So there's the circle of life. The circle of life is a star is born by a collapsing gas and dust cloud. They form. They emit gas and dust over their lifetimes, part of the solar wind that comes off of our sun. And then some of those stars will blow up. And when they blow up, they will compress that gas and dust. First, the existing gas and dust that's out there, but also the gas and dust that the other stars have emitted over their lifetime. And when they compress that gas and dust, they produce more stars. And some of those stars will blow up and compress the gas and dust and produce more stars. And we have the circle of life, and we should all break out in song. Okay? That's the circle of life for stars. So what defines the difference between a star and a protostar? just this. A star is where there are nuclear fusion happening at its core. Nuclear fusion happening at its core. And for a star the size of our sun, that nuclear fusion is the fusion of two hydrogen atoms to helium. And let me show you that. Okay, so reset the animation. So here is hydrogen. The hydrogen combines in fairly complex reactions until the end result is a lot of energy and a helium-4 atom. Okay, so we have 4 hydrogen atoms. They do a bunch of complex stuff, produce a bunch of energy. At the end result, we have helium, which has 2 protons and 2 neutrons. Okay, it is very complex, Corey. There's a story about a famous physicist who was walking down the street in the 1930s, and his girlfriend at the time, and subsequently his wife, pointed up and says, "Boy, aren't the stars beautiful tonight? I love how they shine." And the famous physicist turned to his girlfriend and says, "Yes, I love how they shine too. And right now, tonight, I am the only person on this planet that knows why they shine." Because that very night, he had figured out this very complex path. He'd also figured out an even more complex path that is of only minor importance for our sun, but is of major importance for other sun. That's even more complex. So let's bring that up. And this is called the CNO cycle, the carbon nitrogen oxygen cycle. And you do not know the details of this, just realize how complex the cycle is. So are there just a bunch of positrons hanging out in the sun? No, positrons are instantly destroyed in the sun. So positrons basically never escape the sun because they will instantly combine with electrons and produce gamma rays. Now, there are tons of neutrinos that are produced by the sun. And in fact, hold up your hand. You hold up your hand. In the second I told you to hold up your hand, 100 billion neutrinos from the sun just passed through it. Okay. And we'll talk about more of that later in this course. Okay. So a star is defined by nuclear fusion happening at its core. For our sun, the primary nuclear fusion is hydrogen to helium, and that clips off at 10 million degrees. So the star is a protostar until the core reaches 10 million degrees, and then hydrogen to helium fusion begins. So it's just like a diesel engine. A diesel engine hits its ignition temperature of 2000 degrees, the fuel air mixture explodes, and then it pushes down the piston and we go down the road. Here, the hydrogen waits until it hits 10 million degrees, and at 10 million degrees, the fusion reaction can begin, produce helium and a lot of energy, and the star shines not by gravitational collapse, but the star shines by nuclear fusion at its core, as our sun does. Well, we need to know how nuclear fusion works. No, Robbie, you won't need to know that. You will need to know that the primary nuclear fusion process in our sun is hydrogen to helium. In our sun, it happens through the proton-proton chain. Yeah, actually, you will need to know the proton-proton chain, which is the hydrogen to helium chain. In more massive stars, the CNO cycle is used. How do we know this? We know this because we know that the laws of the universe are true throughout the entire universe. Because if they were different, we would see stars that look different. And we don't. The stars that we see 10 billion light years away are exactly the same as stars that we see right next door. And so we know that the laws of the universe are universal, and they're universal not only on the planet Earth, but they're universal in the stars themselves. And so knowing the universal laws of science, we can then calculate exactly what is happening at the core through using the laws of thermodynamics that govern that diesel engine. Those laws also operate in our sun, and we can use computer models to calculate exactly what's happening at the core through the laws of thermodynamics and the laws of nuclear fusion. Stars are built that are built different. Well, yeah, like I said, with minor exceptions, the if you know the mass of a star, you know everything there is to know about the star. Okay. So the laws of stellar structure, hydrostatic equilibrium, everything has to be in equilibrium, because if it wasn't, layers would be moving up and down. And for the most part, star layers stay in their proper place. Energy transport. The energy must be transported from the center of the sun all the way to the surface of the sun. And the energy transport must balance at every point, because if it didn't, energy would build up at certain layers in the sun. And we know they don't, because our sun doesn't explode. So because our sun doesn't explode, we know that every layer of the sun must transport energy to the next layer at exactly the same rate. So the sun produces one solar luminosity at its core, and it produces one solar luminosity at its surface. And we know that we just state this. We know it must be true because our sun, like I said, isn't blowing up. Now, stars that do blow up, they'll have different equations. And mass concentration, the total mass equals the sum of all the masses. And energy conservation, the total luminosity equals the sum of all the energy produced by all the layers. So all of these are just basic laws of science, laws of logic, and we use those laws to calculate what our sun is like and what stars are like at their cores. And stars are a lot simpler than people, let me tell you. Now, here is a video that was made by some friends of mine at the University of Illinois at Urbana-Champaign Scientific Visualization Center, and it's narrated by someone relatively famous.